Good morning, sir.
Good morning, sir.
Good morning, sir.
Good
The
morning.
last week of online class.
Good morning, sir.
सर मिला आपको टाइम टेबल?
Partly have an idea. Timetable is being made.
सर कैसा इंक्रीज हो रहा है क्लासेस का टाइम, लाइक ईच लेक्चर टाइम इज इंक्रीजिंग?
But they are yet working on. They'll in some batches they'll try hybrid mode. They'll try to keep the camera also inside the classroom. Some students who are keen on listening to it.
Yes.
The digital board system may not work out. Okay, what was the last thing we covered in the previous class?
One sum of from the exercise for moment of inertia sum.
Okay, we didn't start
Where equation of the slope was given y is equals to x square. Not
okay.
slope,
We didn't start the expression for kinetic energy.
No, sir.
we have to start.
Something interesting in today's class. How do you calculate the kinetic energy of a body?
हाफ mv स्क्वायर.
पता है ना यार, half mv square.
Yes, sir.
For any point object, fundamental definition is half mv square. That will never fail you if it is a point object. What if it is a rigid body?
It can rotate also. So rotationally.
Now, first of all, consider subtopic kinetic energy of a rigid body. Kinetic energy of a rigid body or a system of particles. Kinetic energy of a rigid body or a system of particles. Right? Now, M1 particle is at a distance of R1, M2 particle at a distance of R2, M3 particle at a distance of R3, M4 at a distance of R4, M5 at a distance of R5, so on and so forth, up to Mn at a distance of R. Body is rotating with an angular velocity only. Kinetic energy of this body will be summation of mi vi. I goes from 1 to n. Do you agree with that?
Yes, sir.
Yes, sir.
Yes, sir.
The body constitutes small, tiny point objects. So kinetic energy of each point will be half mv square. So half mi vi square. Sigma of kinetic energy half mi vi square. Kinetic energy is half mi vi square, not momentum, kinetic energy, hence half mv square. Right? Now half mi vi will be ri into omega whole square. I goes from 1 to n. See if you are convinced with what I have done. Every particle will be moving perpendicular to its radius. When the body is rotating,
Yes.
this is going in a circular track, this is going in a circular track, this is going in a circular track. So V will be R omega. V will be R omega. But you played it smart here. Vi you wrote as Ri. Omega I.
It's the same for
Rigid body theorem.
Angular velocity or displacement of every point object will be the same. There is an ant here, there is an ant here, there is an ant here, there is an ant here. I turn by 90 degree. Every ant will report the same angular displacement. Right? Sigma of half mi ri square omega square. More appropriately, I will put sigma here and I got half outside. Half is a constant, I can bring it out. Omega is a constant, I can bring it.
Yes, sir.
Can you recognize sigma of mi ri square as
Moment of inertia.
Moment of inertia.
This actually is a replica of half mv square. Mass is replaced with moment of inertia, linear velocity replaced with.
Angular velocity.
Whenever a body is subjected to pure rotation, body in pure rotation, kinetic energy is half I omega square. Now, how do you combine these both concepts? A body can have both translational as well as rotation. Pure rotation, I know. Pure translation, I know. Pure translation is half mv square. Combination of both is a tricky situation and an interesting situation. Take it down to it.
So it is not just the summation of both of the two kinetic energies.
With a small summation only, but with a small precaution. Can I rub the board?
So 1 minute.
Yes, sir.
Now, suppose the body is a combination of translation and rotational motion. The expression for kinetic energy is like this. Kinetic energy of the body about its center of mass plus kinetic energy of center of mass with respect to ground. I repeat this, listen to this carefully. We will use this extensively. Kinetic energy of the body about its center of mass plus kinetic energy of center of mass with respect to ground, or with respect to any point, with respect to which point you need that point. Kinetic energy of the body about its center of mass plus kinetic energy of center of mass with respect to ground. Derive. Have a look at this. This is the origin, my ground. I am finding out the kinetic energy of this rigid body. Consider a small element dm. Right? This is the center of mass of the body. Let us say assume or consider this to be the center of mass. Right? dm distance, call this as r. R dash r, however you are comfortable, you called this to r. dm to center of mass, call this as r dash, call this as capital. Anything with. The derivation is not important for us. Neither do you have it in your HSC, nor will you require the derivation for the JEE entrance. The final end result is important. But why am I deriving it? For you to understand one point. एक point के लिए पूरा derivation करोगे, हाँ. Listen carefully. People are sleeping or yet sleeping. Please wake up. Do I have your attention?
Yes, sir.
So
Now, kinetic energy of this particular body is half dm velocity of the point P with respect to O whole square. Half dm velocity of point P with respect to O whole square. Summation of this is my kinetic. Kinetic energy expression half mv square for every point object will never fail. Point object, you took one small elemental point object in that rigid body. So it will be half mv square. Right? This you will write as half dm velocity of point P with respect to center of mass plus velocity of center of mass with respect to O whole square. Velocity of point P with respect to O is velocity of point P with respect to center of mass plus velocity of center of mass with respect to O. Half dm velocity of point P with respect to center of mass whole square plus half dm velocity of C with respect to O whole square plus half dm. This half will go because of 2 velocity of point P with respect to center of mass, velocity of C with respect to O. What have I done? A plus B whole square, A square plus B square plus 2AB. Right?
Yes, sir.
Now I'll bring center of mass velocity outside. Body is moving either with uniform velocity. Center of mass is either going with uniform velocity or it may be at rest. Right? Now this expression is important. This will turn out to be 0. Why? Velocity of all the points with moment vector summation of momentum of all the particles in the center of mass frame will be
Zero.
dm into velocity of the point P with respect to center of mass. This integration will be,
Zero.
and this privilege is there only for center of mass.
Yes.
So remember, when you are doing this kinetic energy with respect to center of mass plus kinetic energy of center of mass with respect to ground, I cannot do it about any other point. I have to do it only about.
Center of mass.
Why? Because only about center of mass this turns out to be zero. Is the point clear?
Yes, sir.
So can you please repeat?
Only about center of mass, vector summation of momentum of all the particles will be zero.
Yes, sir.
Velocity of point P with respect to center of mass into dm.
Yes, sir.
Now, what is this? Velocity of point P with respect to center of mass. Can I call this to be the kinetic energy of all the particles with respect to center of mass? Kinetic energy of the body with respect to center of mass. This is kinetic energy of center of mass with respect to ground.
Yes.
Right. This is kinetic energy of the body with respect to center of mass. Kinetic energy of center of mass with respect to
Ground.
right. Or to write it much more clearly, let me write the next step as well. This is half dm velocity of point P with respect to center of mass. Velocity of point P with respect to center of mass. Yes or no?
Yes, sir.
Will be r dash square. Velocity of point P with r dash omega whole square plus r. You have taken this CO constant outside. तभी तो ये summation 0 1 है यार. Velocity of center of mass with respect to O is constant. You brought it out. तभी तो this summation conveniently you told me was 0. This is vector summation of momentum of all the particles in center of mass frame. Center of mass is moving with uniform velocity. So VCO is constant. I can write it as half VCO whole square integral dm. Half integral dm into r dash square omega square. Half capital M whole square. Can you recollect integral dm r dash square to be ICM?
Yes.
Half ICM omega square plus half m VCM square. Kinetic energy of any system of particles, will be kinetic energy of the system of particles about its
Center of mass.
kinetic energy of center of mass with respect to.
Ground.
Now, I will stitch two things. Conservation of momentum, what did you tell me? Kinetic energy of a system of particles will be minimum in.
Center of mass frame.
Center of mass frame.
Now you understand, because kinetic energy general expression will be kinetic energy in the center of mass frame plus kinetic energy of center of mass.
Yes.
Kinetic energy of center of mass becomes 0. This will be the minimum kinetic energy, right?
Yes, sir.
Understood this?
Yes.
Yes.
So, bottom line, if derivation is of least interest for us, nobody will ask you the derivation. Why did you do the derivation? For you to feed it in your mind permanently that I can do this only about
Center of mass.
Center of mass.
kinetic energy of the body about its body or system of particles about its center of mass plus kinetic energy of center of mass with respect to ground or point O or any particular thing you need. You will get the kinetic energy of the system of particles with respect to the origin or the ground.
Yes.
Take this down, I'll show you how to use this at the first place. Tell me when I can rub the board.
Yes, sir.
Life is all about perception. How you want to look at it is the issue. I have a point object going in a circular. I have a point object going in a circular. A point object of mass and moving with a velocity v, nobody will have a doubt. They will tell it is half mv square.
Yes, sir.
Got this. But if the same point object is going in a circular track, this is a v. Now, one of you will tell me circular track जा रहा है ना यार, जो भी track जा रहा है speed तो v ही तो है. So kinetic energy you will tell me is half mv square. Now one of you will say, I am now one step ahead. I know circular motion. I will stand here and I will report constant angular velocity. A person standing at the center will see angular displacement for the point object. Right? Now he will say, I will the pure rotation. For this man, this particle is in pure rotation. For this man, this particle is in pure rotation. The man at the center is at rest. The particle is going about in a circular track this way. It is pure rotation. So he will report half I omega square.
Yes, sir.
Don't you think both are different? They are not. Kinetic energy as seen by this particular man is half I omega square. Half. This is a point mass.
Yes, sir.
Moment of inertia is
Yes,
mr
sir.
square. Half m r omega whole square. Same value आ गया कि नहीं?
Yes, sir.
Yes, sir.
Now, when will your trouble come? This is a sphere, Earth going around the sun. Earth has got one kinetic energy, it will rotate about itself. Another kinetic energy, it is going around the sun.
Yes,
Earth has two angular velocities. One angular velocity gives me time period of the day to be 24 hours. Another angular velocity gives me 1 year.
Yes, sir.
Now, how will you calculate this? Have a look at this. This body may be rotating with an angular velocity omega naught about this axis and omega about this. It is going around the circle in 1 year. It's going around itself in 1 day.
Yes, sir.
Yes, sir.
Now, kinetic energy of this body is half ICM omega naught square. Kinetic energy of the body about its center of mass plus kinetic energy of center of mass with respect to this. This is VCM is equal to capital R omega. Capital R is the distance from here till here. Half M R omega whole square. This either you write as half mv square or put it as half I about O into omega square. I am okay with this. Both will give you the same result is what I showed you. So kinetic energy of the body about its center of mass plus kinetic energy of center of mass with respect to
Origin.
right. I will get the total kinetic energy of the body.
Yes, sir.
Is the logic clear?
Yes, sir.
Yes, sir.
I will slightly complicate this version for you to understand this better. Take it down to here.
Yes, sir.
Now just imagine a thin rod hinged this way is released from the horizontal position. It will come to the vertical position. Yes or no?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Please observe. A thin rod released from the horizontal position this way, it will come to the vertical position.
Yes.
I am interested in the omega of the rod. Mass of the rod is m, length of the rod is l. Find the omega when it comes to the lowermost point. Simple. Loss in potential energy should be gain in.
Kinetic energy.
Loss in potential energy should be gain in kinetic energy. Loss in potential energy is gain in kinetic energy. Sounds good. Loss in potential energy also is quite easy for me. mgl by 2 by sir. mgl by 2
Center of mass.
Center of mass.
Chain problems in work energy theorem, you people remember, we used to take
Yes,
whole of
sir.
the mass appear to be concentrated at center.
Center of
Loss in potential energy. Gain in kinetic energy, I have two ways of doing. One, can you recognize the point about which the body is subjected to pure rotation?
So point B.
Sir.
point in.
Hinge. About the hinge, the body is subjected to pure rotation. Yes or no?
Yes, sir.
Yes,
Yes,
sir.
sir.
Half I about O into omega. Half I about O into omega. Pure rotation expression is only so much. Pure rotation expression is only so much. Half I about O is ml square by 3 into omega. Half I about O into omega square. Bro, what is I about O? ml square by 3.
Yes, sir.
Right? L will go, 2 will go, m will go, omega is under root 3g by L. Now, one of the student will say, I could not recognize that it is pure rotation about O. But I will go by the standard formula. What is your standard formula? Kinetic energy of the body about its
Center of
Center
mass.
that's kinetic energy of center of mass with respect to
Origin.
with respect to ground, right? So loss in potential energy, how do you write? Loss in potential energy is gain in kinetic energy. mgl by 2 is gain in kinetic energy, half ICM omega square. Kinetic energy of the body about its center of mass
Yes, sir.
plus half m VCM square. Kinetic energy of center of mass with respect to ground.
Yes, sir.
Kinetic energy of the body about its center of mass plus kinetic energy of center of mass with respect to ground. Omega, will it be the same whether you take about O or about the center of mass?
Yes,
Sir.
Rigid body theorem,
Yes, sir.
right? So omega will be the same. ICM plus kinetic energy of center of mass half ml square by 12 into omega square plus half VCM. Have a look at it. I'll have to calculate this. Velocity of center of mass. This will be L by 2 omega with respect to O. Velocity of center of mass with respect to O plus velocity of O with respect to ground is velocity of center of mass with respect to ground. Velocity of center of mass with respect to O r omega plus velocity of O with respect to ground. I'll get the velocity of center of mass with respect to ground. This is L by 2 omega plus 0 is velocity of center of mass with respect to ground. L by 2 omega whole square. Is this step clear?
Yes, sir.
Yes, sir.
Yes.
R omega with respect to O. Velocity of O with respect to ground is 0. No, this is half ml square by 12 plus ml square by 4 into omega square. Half ml square by 3 into omega square. M and M will go, L and L will go, 2 will go, omega is under root 3g by L. Either you recognize the point about which the body is subjected to pure rotation. Sometimes this point may lie outside the body. This point about which the body is subjected to pure rotation may lie
Outside the body.
The body.
we learn how to recognize that, yes, after 5 lectures from now, right? If you can recognize the point about which the body is subjected to pure rotation, kinetic energy of the body is half I about that point into omega square. Perfect?
Yes, sir.
Suppose I am not in a position to recognize that. This will never fail us. Kinetic energy of the body about its center of mass plus kinetic energy of center of mass with respect to ground is the kinetic energy of the body with respect to ground.
Yes, sir.
Now listen. Same problem, we will tilt it this way. This is a thin rod of mass m and length L, and there is a disc of mass capital M and radius R hinged. This is radius R, this is mass capital. This is a disc. This is hinged only at the center. Hinged only at.
Center.
Now the other situation is same mass m length L, but there is a difference. It is hinged all throughout this length. It is fixed from here till here. This is R, this is mass capital. What is the difference between this and this?
Sure, it can rotate about its own, like,
Here it is hinged only about the center. Here it is hinged from here till here. Agree?
Yes.
I am taking this as C, I am taking this as O, I am taking this as C. When both are released from the horizontal positions, find the angular velocity of both the systems when they come to the vertical position. When this comes here, find the angular velocity. First tell me what you will do and then start solving. Don't be distracted. When it came to the lowermost point, find the angular velocity. Same applies to this.
So can you explain how the second case is attached?
In the second case, it is hinged from here till here. All throughout this length, it is hinged.
Okay, sir.
Here it is hinged only at the center. When both are released from the horizontal portion, find their angular velocities when they come to the lowermost point. First of all, please explain to me, which among the two cases do you think will the body rotate about its center of mass?
So in the first case.
First one.
First,
Visible.
तो पहले वाले में
The first one.
first case, second.
Now, whoever said second, could you explain?
तो पहला नहीं हुआ तो दूसरा.
सर आपने बोला फर्स्ट नहीं है तो सेकंड ही
First
तो
नहीं
दोनों
है
का
तो
logic is the
second
best
होगा,
one.
sir.
थोड़ा ध्यान से देखिए. Firstly, in the first case, the hinge is at the center of the disc, right?
Yes,
Yes.
sir.
Yes.
Do I have any torque about the center of the disc?
No, sir.
Oh,
Torque is 0, alpha is 0.
हाँ, sir.
yes,
Yes, sir.
Alpha is 0, omega should remain constant.
Okay.
yes, sir.
Yes, sir.
Initial omega about its center of mass is 0. Final omega also about its center of mass will be 0. So the disc will not rotate about its center of mass. right?
Yes, I
Yes,
got it.
sir.
People who are not listening to this are missing on the most important part of today's class. On your own, you will not be able to visualize this. First point, there is no torque about the center of mass. So there will be no alpha. So don't tell me there will be no omega. Omega will be constant. If initial omega is 0 about its center of mass, final omega about its center of mass will be 0. That's all that I'm telling you. In this case, there will be torque about center of mass.
Yes.
There will be torque about center of mass. Your normal poles here. About center of mass, you have a torque. That means there is alpha.
Yes, sir.
That means omega will change.
Yes, sir.
You will be able to visualize that. You have fixed it from here till here.
Yes, sir.
हाँ सर
फिक्स कर दिया लॉजिकली टॉर्क अल्फा वर्ड्स बड़ा जबरदस्त यूज करके आप अपना आंसर ले आए मुझे विजुअलाइज तो करवाओ जेन्युइन
Yes, sir.
Yes.
Yes.
हाँ सर करवा दो ना
this is the desk this is the desk my hand is the desk
Yes, sir.
first case it is hinged only at the center my
हाँ,
fingers
सर,
were pointing upwards even when it came down fingers were pointing upwards so about the center of mass did my hand rotate
yes,
No,
no
sir.
sir no sir
now in the second case it is hinged from here till the center from my thumb till here it is hinged
okay sir सुना
did my fingers rotate by
Yes,
an angle
sir.
of 90
Yes, sir.
सर जी सर
Yes, sir.
first case ध्यान से सुनिए my fingers were pointing upwards initially they're pointing upwards finally as well so first case when you hinged it about the center disc did not rotate about its center of mass second case from my thumb till the center it is fixed so the disc will rotate this way did the disc rotate by an angle of 90 about its center of mass
yes sir
Yes, sir.
now are you able to visualize
Yes.
Yes, sir.
I'll put it in terms of numbers. I'll nomenclate them. Have a look at it. Pay attention. I'll call this point 1, point 2, point 3, point 4. When the disk came down, this will remain 2, this will remain 1, this will remain 3 and 4. Here, this is point 1, this is point 2, point 3, point 4. When the disk came down, this is point 1.
yes sir
When the disk came down, this is 2, this is 3, this is 4. Didn't the disk rotate by an angle of 90, in this case, about its center of mass?
yes sir
In this case, about its center of mass, this did
Okay,
not.
Rotate.
Rotate.
Now you understand why rotation is tough. What you visualize many a times will not be true. Right? This visualization is the toughest thing, but actually the toughest topic is EMI. But well, whatever people's feedback is.
So can you show the visualization for the first one again? I'm not understanding.
It is hinged at the center.
Yes, sir.
My fingers initially are pointing upwards.
Yes, sir.
Did my hand rotate about its center of mass?
Yes, sir. Okay, got it.
Now in the first case, how will I do the calculation? Watch out for this. Loss in potential energy. MgL by 2 plus capital MgL. Do you agree that this is the loss in potential energy?
yes sir
Will be equal to the gain in kinetic energy. Gain in kinetic energy for the thin rod, I will conveniently write ml square by 3 into omega square. What have I done? I took about O. We already explained about O. The thin rod is subjected to pure
Rotation.
Rotation.
So half I omega square.
Yes, sir.
Somebody
ML.
wants to find out about the center of mass of the thin rod and calculate, I have no problem with it. This is half I omega square about O plus. Now kinetic energy of the disk. Kinetic energy of the disk, how should I calculate? Kinetic energy of the disk about its center of mass plus kinetic energy of center of mass with respect to ground.
Yes, sir.
Now, what is the kinetic energy of the disk about its center of mass? Kinetic energy of the disk about its COM plus kinetic energy of COM of the disk with respect to ground. Kinetic energy of the disk with respect to center of mass is 0.
Yes, sir.
Right? Kinetic energy of center of mass is half capital M Vc whole square. How much will Vc be equal to L omega? Vc is equal to L omega. Say something, yes or no?
Yes, sir.
Yes, sir.
That means the disk will behave like a point object. Yes, because disk doesn't rotate about itself. If Earth doesn't rotate about itself and is going around the sun, I can consider Earth to be a point object and tell you its kinetic energy is half mv b square.
Yes, sir.
I showed you in the starting of the class. Point object going in a circular track.
Yes, sir.
Here, if this kinetic energy is 0, if the disk is not rotating about its center of mass, it is as good as a point object placed at C. Half mvc square. Kinetic energy of the disk about its center of mass plus kinetic energy of center of mass with respect to ground. What is kinetic energy of center of mass? Whole of the body is placed at its center of mass. Now in this case, it will be mgl by 2 plus capital mgl will be equal to half ml square by 3 into omega square. Till here I am saying this is kinetic energy of what? Thin rod.
Yes, sir.
Yes, sir.
Yes, kinetic energy of the disk half ICM omega square plus half capital M V square. Kinetic energy of the disk about its center of mass plus kinetic energy of center of mass with respect to ground. Kinetic energy of the disk with respect to center of mass. ICM is capital MR square by 2. ICM, this is capital M, this is R. ICM is MR square by 2.
Yes.
Right? VC is equal to L omega. This VC will be equal to L omega. Is the difference clear for you?
Yes, sir.
Yes, sir.
With this and this, key at first point itself, students fall for a trap. They assume this disk rotates about its center of mass. It doesn't. This disk is rotating about its center of mass. So here, how will I write the kinetic energy expression? Kinetic energy of the disk about its center of mass plus kinetic energy of center of mass of the disk with respect to ground. I'll get the total kinetic energy of the disk with respect to ground. One of the most trickiest situation in kinetic energy conservation.
Yes, sir.
Now we are sure we'll be able to handle kinetic energy, right? We'll be able to calculate the kinetic energy of a body about its center of mass and kinetic energy of center of mass with respect to ground, right?
Yes, sir.
Now stay for 1 minute. I will have to see what is this. 1 second. There is some message from face. Okay. Now listen. The next we need to introduce is hinge forces. Hinge forces. Nothing but a normal force. Nothing but a normal force. But there is a difference. In a hinge, what happens is two rings are placed one over the other and a nail is sent in between. Two rings are placed this way and a nail is sent in between. Right? Now, if the nail is pushed to the left, normal force is to the right. Nail is pushed to the right, normal force is to the left. I'll put it this way. Door hinges, I wish I could show you this on YouTube. Door hinges. These people give us strange things. One second. Now, though this guy is showing us how to fit a door hinge, right? But I can explain.